Okay, let's continue the discussion about section 3.3. The next topic, what is this topic? 4, 5. The average rate of change. Of a function. Average rate of change of a function. Change means use a new value minus original value to subtract the original value. That's a change, right? So when you have a interval AB, if it's about x, what is the change from over the interval? So that's b minus a. That's from the initial value to the terminal value, okay? And the corresponding y value will be fb and fa. What is the change about y value? We do the difference. Is the change of y over ab. Well, rate of the change. When you see the rate, you have the quotient, okay? So definition, if a and b, here a, b are different, are distinct, are both in the domain, of a function y equal to fx, the average rate of change, average rate of change of f from a to b is defined as average rate of change. Well, let's not use this. That's a different one. Average rate of change is equal to fb minus fa. This is change of y over b minus a. This is change of x. Here, in the short symbol, we can use a delta y over delta x, the difference of y value over the difference of the x value. Here we emphasize a is not equal to b. Denominator is not 0. Okay, so this is our average rate of the change. And this delta y is the change in y, okay? D. Well, that's a definition. Let's see how do we do computation based on the definition. Find the average rate of change. The average rate of change here. Fx is 3x squared. It depends on the domain, interval. You have a AB, okay? So let's say from 1 to 5. If it's from 1 to 5, A is a 1, B is a 5. So A is a 1, B is a 5. The average rate of change is F5 minus F1 over 5 minus 1. f5 is 3 times 5 squared is 25. f1 is 3 times 1. 5 minus 1 is 4. 3 times 25 is 75. 3 times 1 is 3. So it's a 72 over 4. What's this? It's a 18. So the rate of the change is 18. From 1 to 3, let's check. From 1 to 3. If it's from 1 to 3, A is a 1, B is a 3. So it's f of 3 minus f of 1 over 3 minus 1. F of 3, the 3 times 3 squared. F of 1 is 3 times 1 squared over 2. 3 times 9, 3 times 9, 27. 3 times 1 is 3. It's 24 over 2. It's 12. Okay, so that's the average rate of the change. Let's see. Another B. So far, if we really want to figure out the value, possibly I cannot put some difficult functions. I can only give you the polynomials because it's easy to evaluate. So for example, if we put g of x equal to negative x cubed plus 1, then I say for the required AB from 0 to 2. So A is 0, B is 2. So it's a g of 2 minus g of 0, 2 minus 0. FB minus FA, B minus A. Always this. FB minus FA, B minus A. So g of 2 is a negative. 2 cubed is 8 plus 1. This is a GB minus GA. It's a 1. Right? 1A is 0. G of 0 is a 0 cubed plus 1. Okay, this is a negative 8 over 2 is negative 4. And if we get from negative 1 to positive 1, let's see. So A is a negative 1, B is a positive 1. So this is a G1 minus G negative 1 over 1 minus negative 1. G1 negative 1 plus 1 minus G negative 1. Negative 1 cubed is negative 1. Negative of negative 1 is positive 1. Negative 1 plus 1 is 0. So it's minus 2 over 2 is negative 1. Okay, so that's our average rate of the change. Just follow the definition, okay? You don't have any difficulty to do the evaluation. You do the evaluation and do the quotient. There's one concept, geometric concept, related to this average rate of the change. It's called the second law. What is the second law? So for example, you have a graph of a function like this, and the second line means that the line contains 2 points from the graph, like this. So let's first give the definition. What is the second line? The line containing 2 points from the graph is called a second line, or the second line. Okay, 2 points. So you have you have this point A, FA, and this point b fb, and function is y equal to fx, afa bfb. Okay, you have a line. Whenever you have a line in geometry, one of the important quantity is the slope. With 2 points, how do we compute the slope? The slope read it. Yes. The slope of the second line is, what is the slope? Slope is rise over run, right? So let's check. Rise fb minus fa. Run b minus a. So the slope is rise over run is fb minus fa over b minus a. So that's a geometric concept. Check this. This is exactly the average rate of the change. So theorem, slope of the second line the average rate of change of a function from A to B equals the slope of the second line containing the 2 points AFA and BFB. Okay, so that's the theorem. The slope of the second line is equal to the average rate of the change. So in the examples, you can say, let's try to find the average rate of the change from one point to another point. Or you can also say, let's try to find the slope of the second line from that point, the same pairs of point. It's just the same quantity but with 2 explanations. Okay, so let's check. Suppose g of x is equal to 3x squared minus 2x and plus 3. And first, find the average rate of change of g from -2 to 1. So -2 to 1. And second, find an equation of the second line. Find the equation of the second line containing negative 2g of negative 2 and 1g of 1. Okay, well, the rate of the change, average rate of the change, g1 minus g negative 1, 1 minus negative 1. And g1, 3 minus 2 plus 3. G negative 2, 3 times 4 minus 2 times negative 2 and plus 3. 1 minus negative 2, right? And you simplify it, you will get, so 3 minus 2 is a 4, 1 plus 3 is 4. And you compute this, you will get 19. It's 12, 12 plus 4 is 16, plus 3 is 19. So this is a negative 15 over 3 is negative 5. So that's our average rate of the change. That's the slope of the second line. So the slope of the corresponding second line is negative 5. The slope, we only talk about slope. And you have a slope, you have 2 points, so you're going to pick up 1 point. So choose. I'm going to choose this 1g of 1 because this value is easier. So 1g of 1, which is 1, 4. Then we have a point slope. Point slope y minus 4 is equal to negative 5 x minus 1. Y minus 4, negative 5 x minus 1. So y minus 4 is equal to negative 5x and plus 5. You move 4 to the right side, it's negative 5x and plus 9. That's it. That's the equation of the second line containing the point negative 2, g of negative 2, and 1, g of 1. Right? So in this part, in this short video, we only discuss technically one computation, average rate of the change. That's one computation. But this computation can be considered as a computation of a slope of the second line through to given point. And when you have the slope, you use point slope form to write down the equation of the second line. That's important. You should be able to write down the equation of the second line based on the average rate of the change plus additional point. Anyone. You can choose this 1, 4. You can also choose a point negative 2 g of negative 2. The textbook choose a negative 2 g of negative 2. It's the same. After simplification, you get the same value. But at the point slope form, of course, they are different. Point slope form is different from here, but the final one is the same. Okay, so we finish this short section. We will continue another section in a different video. Okay, thank you. Okay, today let's continue the discussion. We start section 3.4, library of functions, piecewise defined functions. Okay, so basically in this section we will collect some commonly used functions and memorize their graphs and the basic properties. Okay, so the first is a square root function. So we have y equal to square root of x. Y equal to square root of x. If you, we can only label some special point. We know that we can only take square root for positive numbers, so that's why we just need the positive part. When x is 0, y is 0. So you have 0, 0. When x is 1, y is 1. So here you have 1, 1. When x is 4, we know square root of 4 is 2. So 2, 3, 4. This is 1, this is 4, 2. When y is 9, square root of 9 is 3. So 5, 6, 7, 8, 9. So 3. So we have 1, 1, 4, 2, 9, 3. The points x, y coordinate, and 0, 0, of course. 0, 0. And you connected them. So you will get the rough idea of the graph of a square root function. It's like this. If you want the exact graph, you need to use the computer. Okay. So anyway, from this graph, we can have the list of the properties of a square root function. So property 1, the domain of square root of x is from 0 to positive infinity. It can be 0, square root of 0, 0. It can be positive, but it cannot be negative. The range of square root of x. What is the range? You just read the vertical possibility. So vertically, it's from 0 to infinity. It can be a huge, large number. So the range of square root of x is also from 0 to positive infinity. Okay, so that's the domain range. And the second, the x-intercept. The x-intercept is the intersection between the graph and the x-axis. So there's only one intersection point, that's 0. The y-intercept. The y-intercept is the intersection of a graph and the y-axis. Here is also 0. Okay, and for the property of functions, we have the even-odd properties. But whenever you can define the even-odd properties, the domain should be symmetric about the 0. Here, you only define for the positive number. You don't have any possibility for the definition of a negative number. So this function square root of x is not even, not odd, because its domain itself, the domain is not symmetric with respect to 0. Okay, and 4, square root of x. You see here it's rising. The graph of the function is rising when I move from left to right. So square root of x is increasing. On the domain 0, infinity. Increasing, it's rising. Decreasing, it's going down. 5, the function has a lowest point. You see, this point, it is the lowest point. The lowest point gave us the absolute minimum. Has an absolute minimum at x equal to 0. The absolute minimum value is also 0. Okay, so it has absolute minimum. It occurs at 0, and the value is also 0. This is f of 0. This is actually equal to square root of 0. Here is x value. This is about y value. Okay. Okay. So this is the basic square root, the basic property of the square root function. You have domain range. You have x-intercept, y-intercept. You have even odd. It's not even, not odd. It is an increasing function, and it has absolute minimum value. It does not have absolute maximum value. Okay. Square root function. Second, let's check here. In the first example, we studied the square root, and we can study the cube root. The cube root function if we follow the same thing, we can see that for 0, cube root of 0 is 0. For 1, cube root of 1 is 1. And the cube root of -1 is -1. This is because -1 cubed is -1. Okay, so the cube root is the inverse function of a cube function. And cube root of now it's not 9, it's 8. Now I have to use 8. Cube root of 8 is 2. And the cube root of -8 is -2. Okay, so you see here we allow negative numbers because the cube root has cube root is defined. Cube function has a negative number in the range. Okay, so let's label them. So we have 1, 1, 2, 3, 4, 5, 6, 7, 8. 8 we get a 2. It's even more flat. Okay, so yeah. And for -1 it's -1. So here. -2, -3, -4, -5, -7, -8, 6, 1, 2, 3, 4, 5, 6, 7, 8. 8 is here. -1, -2. Okay. Okay, so the graph of cube root function is more or less like this. Okay, so you can see that we have the similar list of the properties of a cube root function. Property 1, the domain of cube root is -infinity, +infinity. It is defined over the whole x-axis. The range of cube root of x is also from -infinity to +infinity. Even though here we see it is very flat, but actually it can approach -infinity and +infinity. Okay, and then the x-intercept. X-intercept is the intersection between the x-axis and the graph. You see here there's only one intersection. So x-intercept is 0. Y-intercept. Y-intercept is intersection of the y-axis with the graph. It's also 0. Okay. 3. This graph, you see here, if you rotate the right branch pi radian or 180 degrees, you get left branch. So the graph of cube root of x is symmetric with respect to the origin, and the function is odd. Odd function, the graph is symmetric with respect to the origin. This is an odd function. Odd function here, f -x is -fx. This is definition. If we use the cube root function, the cube root of a -x is negative cube root of x. Okay, this is an odd function. And the function is always increasing. If you move from left to right, the graph is rising. So the cube root of x is always increasing. And you see here it's from -infinity to +infinity. So this cube root function has no any local extrema. Local extrema means it has no local maximum or local minimum. For whatever point its right point will be higher than it, its left point will be lower than it. So it's not local max, not local mean. Okay, so it's not like the square root function. Square root function, check here, square root function, you cut it, you only have half, so half branch. So it's it has an absolute minimum. Okay, so this is a cube root function. And next, we study the absolute value function. What is the absolute value function? Y is equal to absolute value of x. So absolute value of x, when x is a positive or 0, absolute value is itself, like absolute value of 2 is 2. When x is negative, we will drop this negative sign, but when you use x to represent this negative number, there's no negative sign. How do we drop the negative sign? We actually use an additional negative sign to balance it. So negative 2, you put additional negative sign, it becomes positive 2. This is used to define the absolute value for the negative numbers. Okay, so when x is negative, negative x is positive, and it is the absolute value of x. Okay, even though it contains a negative sign, but because x itself is negative, with this negative sign, you do have a positive value. Okay, so this is the definition for the absolute value function. And if we graph it, for 1, you have 1, for 2, you have 2. Actually, this time we can use whatever number, like 1/2, you have 1/2, 2/2, you have 2/2. So it's a diagonal. And for the negative part, when you have negative 1, you have positive 1. When you have negative 2, you have positive 2. The value, I'm talking about value, so it's also the diagonal. So the graph of absolute value of x is like this. Absolute value of 0, 0. Okay, so let's see the property. So first, the domain. The domain is negative infinity to positive infinity. Any number has its absolute value. The range. The range you see here is always above the x-axis, including 0. So it's from 0 to infinity. So the range of absolute value of x is non-negative. Second, the x-intercept. X-intercept, it intersects, the graph intersects x-axis at 0. Y-intercept. Y-intercept, you see the intersection of the graph with the y-axis is also 0. Okay, this function, absolute value function is even function because you put absolute value, you put a negative sign, you don't put a negative sign, you never change the value. Okay. Because you have an even function, the graph is symmetric with respect to y-axis. The graph is symmetric with respect to the y-axis. And you see here the left branch, the graph is going down. The right branch, the graph is going up. So absolute value of x is decreasing on negative infinity to 0, increasing on 0 to positive infinity. The left part is decreasing, right part is increasing. And the final property, absolute value has the absolute minimum value 0 at 0. So this 0 is y value, this 0 is x 0, x equal to 0. So value is y. It happens at x equal to 0. Okay, that's the absolute value function and its graph. Okay, so to summarize the section, we have the following list. We already studied many functions, so we have now let's just list them and we review. So first, we have a constant function. Constant function f(x) is equal to b. B is a constant. Its graph is like this. Constant function, the graph is horizontal. Its position depends on the value of b. If b is positive, it's above x-axis. If b is negative, it's below the x-axis. If b is 0, it is x-axis. Okay, so this is a constant function. And second, identity function. Sorry, identity function. Identity function is f(x) is equal to x. The graph is a diagonal of first and the third quadrant. Okay, identity function. And another is a square function. Square function f(x) is x squared. Its graph is a parabola. Graph is a parabola. And then you have a cube function. f(x) is x cubed. Square function on the left branch, it is decreasing, right branch is increasing, and it has a absolute minimum value. A cube function is always increasing. It does not have any local extrema. Okay. All these four functions have the domain from negative infinity to positive infinity. Okay. And this one, the range is from negative infinity to positive infinity. The constant function, the range is a point. Square function, the range is from 0 to infinity, including 0. For cube function, the range is from negative infinity to positive infinity. And then we also have the square root function, cube root function, as we just discussed. And another thing is a reciprocal function. Reciprocal. Reciprocal function is f(x) equal to 1 over x. Reciprocal function, the graph has two pieces. Okay, the right and left branch. Because 0 is undefined, so the graph does not intersect the y-axis. So this function has no y-intercept. Because y-intercept is always f of 0. The function must be defined at 0. Here the function is undefined at 0, no y-intercept. And the reciprocal function has a domain negative infinity to 0, 0 to positive infinity, excluding 0. The range is also from negative infinity to 0 and 0 to positive infinity. So they have the same domain and same range. And also we have the absolute value function. And the next interesting function is called the greatest integer function. The greatest integer function, so we call f(x) is integer of x. So you see this symbol. And the definition means it's a greatest integer less than or equal to x. Okay, so this is a greatest integer less than or equal to x. We use this symbol int of x. And in some other textbook, you will see this type of symbol. It's like the ops value function, but you have two horizontal segments here. Okay, so this is a greatest integer function. Let's see the check some example. For example, if we have integer of 1.5, the greatest integer less than it. So 0 is less than it, but 1 is also less than this 1.5. So 0 is not the greatest integer. But 2 is not less than it. So the integer of 1.5 is 1. And similarly, integer of 2.4 is 2. Okay? So for the positive number, you just check the positive part, integer part. For the positive decimal number, you check the integer part. That will be the greatest integer. And if you have 1, the integer part of 1, you see here in the definition, we allow this value equal to x. So 1 is equal to 1. That is the largest possible, the greatest possible integer, less than or equal to x. So for the integer part is the integer itself. And same thing, if we put a 10 here, it's 10. If we put pi, remember pi is a 3.14, so the integer part of pi is a 3. And the integer part of 0 is 0. The interesting and the tricky point apart for the greatest integer is this one. If you have a negative 1.5, the greatest integer is not negative 1, it's negative 2. Because negative 1 is not less than negative 1.5. Negative 1 is greater than negative 1.5. Okay, so be careful about negative part. So if you have the number line, this function will be more clear. Okay, so 1.5 is here. The left integer close to it is 1. So this is our greatest integer. Okay, so 1.5 is here, the left. And the negative 1.5 is here. Negative 1.5 is here. So the left integer to it is negative 2. So you're looking for the left integer or itself. Okay, so if you have a negative integer, it's still itself. Integer, the integer part is itself. But for the negative decimal number, when you check for the greatest integer, you should be extremely careful. So it's always the left integer. Okay. So for example, the integer of negative pi. Pi is the 3.14. Negative 3.14. It's a negative 4. You see, it's a negative 3 here. Negative 4 is here. Negative pi is possibly like this. So you check the left point, left integer is here. Okay, so if you are confused about the greatest integer function, draw the number line, label the point on the number line, and see the left integer, the left one, because we use less than. Okay, now let's see the graph. What is the graph of the greatest integer function? Okay, let's put 1 and 2. When you have 0, the value is 0. When you have 0.1, you see 0, the greatest integer is 0. Let's use int of 0. 0.1, the integer part is 1. 0.9, the integer part is 0. Sorry, 0. So over this whole segment, the value is constant 0. But when you reach 1, it becomes 1. So the value at point 1 is equal to 1. So you have to start from this point. And then integer part of 1.1 is 1. Integer part of 1.9 is also 1. So you reach here. But at 2, it's here. So it's like a stair function. And similarly, for whatever, this is -1. For whatever point from this segment, the left integer is this -1. So it's a -1. But at 0, it's 0. So this step function, the left endpoint is included into the step. The right endpoint is always the next on the next step. Okay, so that's the graph. It's an infinite step function, infinite. So that's the greatest integer function and its graph. Okay, so the greatest integer function, absolute value function, their definitions actually can be defined with a piecewise technique. So for this interval, we have this definition. For another interval, we have a different definition. So this is the piecewise defined function. So when a function is defined by different equation on different parts of its domain. It is called a piecewise defined function. Piecewise defined function. So like the ops value function. Ops value function is a best example. So for the positive part, the formula is x. For the negative part, the formula is -x. So this is a piecewise defined function. And the step function, this greatest integer function, remember that our definition is this sentence, greatest integer less than or equal to x. But the step function can also be defined by this. When x is, let's put the dot. When x is between -1 and 0, it's equal to -1. When x is between 0 and 1, it's 0. When x is between 1 and 2, it's 1. So it's an infinite piecewise defined function. You can define it over this interval, it's this value. Over the second interval, it's the second value. Okay, and that's the definition from the piecewise defined function for the greatest integer function. Okay. Okay, now let's see an example about these piecewise defined functions. So fx is defined by this -2x plus 1 if x is between -3 and 1. When x is equal to 1, the value is 2. When x is greater than 1, the formula is x squared. Okay, so over different interval, the function has different representation. So first, what is f -2? We do the evaluation. -2, you have to examine where is -2. Negative 2 is included in the first expression between negative 3 and 1. So when x is negative 2, you're supposed to use negative 2x plus 1. So it's a negative 2 times x plus 1. Negative 2 times negative 2 is 4. 4 plus 1 is 5. So f of negative 2 is 5. And f of 1. When x is 1, fx is 2. So you just read it from the definition of a piecewise defined function. And f of 2. F of 2. 2 is greater than 1, so the function is x squared. So it's 2 squared. It's 4. Okay, so that's the piecewise defined function. Okay, and what is the domain? X is between negative 3 and 1. X can be 1. X can be greater than 1. So the domain is negative 3 to infinity. So basically what you do the following thing. You have negative 3, you have 1. 1 is included, and from 1 to positive infinity. So that's together. It's from negative 3 to infinity. You draw the, you label the intervals over the x-axis, and you can determine the domain. Okay, and C, intercepts. Intercepts. So first you check the y-intercept. Y-intercept is f0. Y-intercept is always f0 if it is well defined. So when x is 0, it's in the first case, so it's a negative 2 times 0 plus 1. So use the first formula, so it's equal to 1. The y-intercept is 1. X-intercept. X-intercept means you have to solve fx equal to 0. You have to solve fx equal to 0. You just study here. X is greater than 1. X squared is greater than 1. So for this case, fx cannot be 0. When x is greater than 1, x squared is greater than 1. So it cannot be 0. When x is 1, the value is 2. It cannot be 0. So if the x-intercept exists, it must occur in the first situation. So you're going to use the first formula. So you get a negative 2x plus 1 is equal to 1, equal to 0. So 2x is equal to 1. X is 1/2. Okay, so x is 1/2. It's exactly inside this domain. 1/2 is less than 1 and greater than negative 3. So the x-intercept is x equal to 1/2. Y-intercept is 1. Okay, so this is our intercept. And then we check the graph. Let's check the graph. The graph, you have negative 1, 1, 0, negative 1, negative 2, negative 3. Okay, so we only care from negative 3 to positive infinity. The left part, there's no definition. And negative 2 plus 1. Negative 2 plus 1 is a linear function. Its graph is a straight line. So when x is negative 3, based on the definition, you get y is equal to 7. So 1, 2, 3, 4, 5, 6, 7. And when x is 1, y is negative 1. This part, remember this part, we have definition negative 2x plus 1 over this domain. Negative 2x plus 1. So 1x is 0, y is 1. So my label is not exact. Okay, so it's like this. And when x is 0, x is 0, y is 1. So we must let the straight segment pass through the point 1. And when x is 1/2, it is intersect the x-intercept, y-intercept, x-intercept. And when x is 1, y is 2. So x is 1, y is 2. So this point, you must put a circle. Circle means this endpoint is excluded. Okay, so left part, x equal to 1, x is greater than 1. X is greater than 1, it's x squared. So when x is 1, square function is like this. Okay, just observe the square function and take this part. Okay, so here again we use a circle to represent. The graph does not include this endpoint. So this is the graph of the piecewise defined function fx. And from here we can see that this okay, so here it go to infinity. This function has no local extrema. It has no absolute minimum. It has a local extrema here. Okay, so it has no absolute minimum value because this value is not achieved. It's a circle. It's excluded, so it has no local extrema. Okay, so that's the graph, and also the function. This is D and E. Not E. Let's put E here. The graph is not continuous. So here we cannot give a detailed discussion about continuous, but basically we just say what does this mean? This means the graph is not connected. There's a hole, there's a jump, whatever stuff. The graph is not connected, continuous, connected. Okay, so that's the sketch of the graph of a piecewise defined function. Piecewise defined function, you just over this interval sketch the corresponding equation. Over the different interval, you sketch different equation. Okay, so now let's see a word problem. I'm going to copy the problem. In the summer of 2009, Duke Energy supplied electricity to residents of Ohio for a monthly customer charge of $4.5 plus 4.2345 cents per kilowatt hour. It's kWhr. For the first 1,000 kWhr supplied in the month, and 5.3622 cents per kWhr for all usage over 1,000 kWhr in the month. Okay, so that's the policy. So if you use less, you pay less with a cheap price. If you use more, you will pay with a expensive price for the exceeded the usage. Okay, so within the first 1,000 kWhr, the price is 4 point stuff. Over 1,000 kWhr, each kWhr, the price is 5 point stuff. Okay, so that's the policy. Okay, now let's see the question. Question 1. What is the charge for using 300 kWhr? Okay, the charge for using 300 kWh. 300 is less than 1,000, so the charge comes from two parts. The first part is a customer charge, it's $4.5, and the second part is every kWhr you have a 4.2345 cents. Cents is $0.01. So we use this product to change the cent to be the dollar. We use the dollar, and then you times 300 kWhr. Okay. So that's the computation. You use the calculator. It's about $17.20. Okay, so you have to unify the units. This here you use dollar, here you use the cents. You change the cents to the dollar by multiplying 0.01. Okay. What is the charge for using what? For using 1,500 kWhr. Okay, so the charge is first the same thing. The fixed fee, $4.5. The first is this 1,500 kWhr exceeds $1,000, 1,000 kWhr policy. So first, this is the price in dollar. First 1,000 kWhr, you have the price 4.2345, and after $1,000, 1,000 kWhr, you have 500 kWhr. The price is 5.3622 cents per kWhr. Okay, so for this 500, you have the different price. Here you have one price. Here you have a second price plus a fixed fee. By the calculator, you will see it's possibly $73.66. Okay. So develop a model to relate the charge and kWhr usage X. Okay, so we are going to develop this the general formula. How do we generally study this? So how do we study it? The charge is, if it's less than 1,000 kWhr, you have 4.5 fixed fee plus 4.2345 times 0.01 and times X. Okay, so if you use less, you have fixed fee plus the price, cheap price times the usage. If you use more than 1,000 kWhr, you have fixed fee. The first 1,000 kWhr, first 1,000, you already use more than 1,000. So the first 1,000 kWhr electricity, you have this price. After this, This is the usage after 1000 kWhr. You have the price 3622 0.01. Okay, so this is the case when x is greater than 1000 kWhr. Okay, so this is piecewise defined function. In this range, you have this price policy. In this range, you have different price policy. Okay. So in this section, we basically just review or collect the information about the commonly used functions, and we sketch some graphs. We have ops value function, we have the so-called the integer function, we have the piecewise defined function. And for the piecewise defined function, just focus on the given interval and study the corresponding formula and try to connect or sketch the graph. Okay, so this is the graph, the section 3.4, and later we will study how to graph some complex function from those basic functions. Okay, we'll stop here today. Thank you. Bye.